Hey everybody, welcome to another exciting video lesson. Today we're going to look at periodic trends. Okay, I'm going to do this in two videos. The first video, what I'm going to do is I'm going to talk just about the trends, just telling you what the trends are, no explanation, just boom, we're going to go right through what they are. And then the second video, I'll come back and I'll explain why we see what we see happening in the first video. So first video, what happens. Second video is our explanations. Okay, so here we go. Let's get started. So there's a number of periodic trends we're going to be looking at. One we're going to look at is atomic radius, and you probably remember this from honors chem. Okay, we did atomic radius, ionization energy, and actually we did all of them except for electron affinity. That's the only one that's different. It doesn't show up too much on the AP test, but again, you should be aware of how electron affinity is different than ionization energy and electronegativity. Alright, so let's briefly run through these. Atomic radius is simply the size of the atom, how big the atom is from the nucleus, from the center of the atom, okay, to the electron in the outside. So it's the diameter or the distance between the inside and the outside of the atom. So it's the distance from here to here essentially, and that's going to give us our radius. And I don't have to worry too much about that. Just understand that atomic radius is how big the atom is going to the valence electron, and that's where things can get a little abstract because we don't really know where electrons are because they're in orbitals, but we can make some pretty good approximations. This little crazy symbol here is called the angstrom, and it's 10 to the minus 10 meters. It just happens to be very commonly used when we deal with atomic structures and sizes of the atoms. Okay, nanometers typically used here as well. Not so much worried about the measurements themselves as you are the overall trend. And as you can see, as we go from left to right on the periodic table, the overall size of the atom it decreases from this side to this side. So we move from left to right, we see that the atomic radius decreases, and as we go from bottom to top, the atomic radius decreases as well. So we see another decrease in our atomic radius. Okay, so essentially the smallest atom is going to be helium, and our largest atom is cesium. Okay, yeah, it would be cesium. All right. Now, again, I'm not going to explain anything. I'm just going to purely telling you what the trend is. Okay, so atomic radius decreases to the top right side of the periodic table. Bottom left, atomic radius is going to get bigger and bigger. Okay. All right, so if you have a periodic table, and you should already have one, you might want to sketch this stuff out. At the very end of this video lesson, I will recap all of these. But what you want to do is you want to write these trends so that you know what they are on your periodic table, so that when you're looking at it and you're reviewing, it's all laid out there. If you had me in honors chem, you probably have our periodic tables that we used in the past, so you might want to dig those out. If not, you can always start from scratch. All right, so let's take a look at the next one. The next one is ionization energy. Okay, and by the way, when you're doing these periodic trends, it's really, really important. Is what students always overlook is defining what the ionization energy is. What does atomic radius mean? What is ionization energy? What is electron affinity, and what is electronegativity? What you define those first. Okay, really can't stress that enough because a lot of students just want to blindly memorize these things, and I'm telling you, if you just understand what ionization energy is, you can figure out what the trends are based on what I'll talk about in the second video. Alright, so anyway, ionization energy is you got the protons here, you got your electron, which is negatively charged here. Ionization energy is essentially the energy needed, okay, the energy that we're going to supply to make that electron leave the atom, to knock it out, to ionize the atom, ionization energy. Okay, the reason why they have this from gaseous atom is that if we start with a solid, we have to get it to a gas phase, so that's going to require more energy. So to make everything unified, everything has to start in the gaseous state because states of matter have certain amounts of energy in them. Okay, so we add energy. This is our ionization energy. How much energy is needed to knock an electron out of the atom? And as you can see, our noble gases are at the top. So they require the most energy to knock those electrons out. So as we go from left to right, now this would be hydrogen down here. Okay, hydrogen would be down here. So as I go from hydrogen to helium, ionization energy goes up. This is the opposite that we see from the atomic radius. And if you think about it, it kind of makes sense how they go hand in hand. Then we go from helium down to lithium. Notice there's a huge drop in our ionization energy. So as I go from helium to lithium, or if you take a look at this, if I go from helium to neon, now I'm going down a group. And notice what happens to ionization energy. It requires less energy to knock those electrons out. So when we have helium neon right here, there's a huge amount of energy required to knock those electrons out. So therefore, that's where stability comes from. That's when we talk about chemical stability. It's really not the octet. It's really not anything else other than energies. Okay, and the energy needed to take the electron from, or to knock it out from helium and neon requires tremendous amounts of energy. Whereas when we get to argon and krypton and xenon, notice that the energy is decreasing. It's still stable, but we now have energies that are now going to get into the realm of chemical reactions. There's no chemical reaction that can really pull these electrons away from helium and neon. When we get down here, the energy is low enough that we can now have some chemical reactions. There are compounds with xenon and krypton in them. I'm not sure about argon, to be honest. I don't really remember seeing any compounds with argon, but I definitely know that krypton and xenon, more specifically xenon. We don't really see anything with radon because it's a little more reactive and too big. But anyway, xenon, you'll definitely see some compounds for. So as we go down a group or family, ionization energy decreases as we go from left to right. So we're going from left from lithium to beryllium to boron to carbon and nitrogen, oxygen, all the way to neon. We see that the ionization energy steadily goes up. Okay, so that would be our trend. Our trend on the periodic table as we go from left to right. From left to right, ionization energy increases. Okay, we see an increase. As I go from top to bottom, I have an increase in my ionization energy as well. Okay, so that's the trend that we see in ionization energies. And again, I'm going to come back and explain it, and I'll explain these little anomalies later. All right, the other thing you need to know with ionization energies is something called multiple ionization energies. Okay, because when we have an element like sodium, sodium has 11 protons and 11 electrons. Okay, so when we're looking at the configuration for sodium, there's electrons in the n equals 1, and there's electrons. I'm just going to break it down into half circles here. N equals 2, and then n equals 3. Well, for sodium, its valence electron is out here. So what we're talking about with multiple ionization energies is we're removing more than one electron. So we hit this with some energy, and we knock out the electron. That's the ionization energy that we call the first. And that would be this one right here. So it takes 496 kilojoules of energy to knock this electron out of sodium. Now if that electron is gone, the next electron is in the next energy level 2. So now we hit it with more energy. What we find is when we hit it with more energy, the second ionization energy, look at, huge dramatic increase. It goes up by a multiple of almost 1,000 there. Right? So a huge increase from here to here, and this again explains stability. Sodium's electron, its valence electron, is really easy to lose because of the, well, I'll get into the explanations a little bit later, but for right now it's because it's in that higher energy level. But then we see a dramatic increase in the ionization energy when we go to the second one. We hit those core electrons. Same thing for magnesium. Magnesium is going to follow the same pattern, but in its outer shell, I'm not going to draw the whole thing, but I'm just going to draw the n equals 1, n equals 2, and n equals 3 for the magnesium element. You have 2 valence electrons. And these electrons, when we hit them with energy, that would be my first ionization energy 1, and then that electron's gone, ionization energy 2 knocks out the second electron, and we're still in that same energy level, so therefore first electron, second electron, and then we hit that core. So what this is showing us is our core electrons where there's a break. So this would be the first electron, which is easy to move, first and second electrons, which are easy to move, and notice the third one, huge increase. First, second, third, and then boom, a huge increase. And that is multiple ionization energies. Okay? All right, let's move to electronegativities. With electronegativity, this is a measure of the element's ability to attract electrons in a chemical bond. So keep that in mind. This is talking about in a chemical bond. So this is when you have hydrogen and fluorine, right? We talked about this last year in honors or whenever you had it, that they're sharing these 2 electrons, but fluorine is sharing a little bit more, well, actually a lot more, and we end up with that partial negative, partial positive charge, where the electrons are moving towards the fluorine. It's a higher electronegativity. So the electrons that they're sharing are not shared evenly. And fluorine has the highest electronegativity. And I notice we drop out the noble gases because of the fact that the noble gases, don't take part in chemical reactions. So we're not concerned about them because they're not in a chemical bond. Yes, xenon and krypton, as I said, can be in bonds, and if they are, we'll apply it. But for the most part, we just stop at the halogens. So fluorine is the most electronegative element, so it's going to be the best at pulling the electrons, while cesium is going to be the weakest. So again, you can kind of see that trend from left to right. Electronegativity increases, so it matches our value that matches the change that we saw for ionization energy. And the same thing here, increases as we go in this direction. So we have another increase. So the most electronegative element would be fluorine. The one with the highest ionization energy would be fluorine, and the smallest would be fluorine. Okay, so that would be your electronegativity. This is really important. We use this one quite a bit, especially when we get into bonding in the later half of this unit. All right, let's see what's next. Next should be electron affinity. All right, now I'm going to tell you right now, this one's the one everybody has a lot of trouble with because it's very confusing in the way it works. But here's what it is. It's the energy change that occurs when an electron's added. So it's the opposite of ionization energy because we're adding the electron to a gaseous atom as opposed to taking it out. So what this is measuring is it's kind of like measuring electronegativity, the atom's ability to pull the electrons. But the difference is that there's no chemical bond. We're just talking about a gaseous atom. So that would be something like chlorine. Obviously, chlorine would be diatomic, but we'd be looking at each chlorine atom's ability to take an electron into its structure. Where would it get that electron? It would get it from sodium, because sodium isn't going to be very good at pulling the electron, and therefore it will lose it to the chloride ion. Okay, so actually, you know what, real quick, I just want to briefly talk quickly about electronegativity. Notice that even the metals, we think of metals as giving up electrons. They don't. Metals don't give up electrons. They're holding on to them as well because they have a nucleus just like the nonmetals do. The thing is that when we put a metal next to a nonmetal, the electron's lost to the nonmetal because the nonmetal is so much better at pulling electrons. And that's the idea behind electronegativity and electron affinity. Electron affinity is just looking at it before the bond is made, because after this effect happens, after the electron moves to the chlorine, what you're left with is a sodium ion and a chloride ion that then bond together to make sodium chloride, and that's your ionic bond. So this is where we're going to use this when we talk about the formation of ionic bonds in the later section. Now these negative values, and this is why it's confusing, is the amount of energy released. If you remember in honors chem, this is exothermic, right? If you have a reaction that is releasing energy, we say it's exothermic, energy released. So therefore, when an atom takes the electron in, it will release energy, and that's favorable, that negative energy. Okay. Now, one thing you want to look at is that atoms that are half filled, with that, we mean by that is sublevels and energy levels, it's going to be unfavorable. That means that the energy is going to be positive and not negative. We're not going to get a negative value for our value for the change in energy. Okay, because it's not favorable to put it in there. We'll take a look at why that is a little bit later, but for now we're just looking at the values. So here's the data. We usually only look at the alkali metals, the s orbitals, and the p's. Okay, we don't really look at anything else when we're talking about electron affinity. Now, if we take a look here, fluorine, when it takes an electron, it's going to give off 328 kilojoules of energy. So what that tells me is that fluorine is very good at pulling electrons, hence why we see that in electronegativity. So it kind of matches. Okay, but notice here that sodium has an ability to pull electrons as well. It actually is going to be negative in its ability to pull those electrons, and as opposed to something like here, this is positive. So it's hard to put an electron into the alkali metals. Now the trend for electronegativity is a little hard to see because it kind of changes as you go along. There's some anomalies we'll look at, but overall, as we go from left to right, just like we saw with ionization energy and electronegativity, it's going to increase in this direction. Okay, notice noble gases, it takes a positive because they're stable, and we have to add that new energy level for that to happen. So again, pointing to the fact that noble gas stability comes from energy. So we saw that it was hard to remove an electron with ionization energy, and we see that it's hard to add an electron due to electron affinities, and therefore stable. Okay. All right. So do your best with electron affinities. Don't get too bogged down with them. I know they can be confusing, but we'll talk more about them in class, and I'll try to explain them more. All right. The last thing I want to talk about is Ionic Radius. Okay. And this is real simple. I mean, basically, we're going to take the element, we call this the parent atom, okay, and then we have our ion. So lithium is always going to become a lithium positive. It's never going to take an electron due to the fact that it's going to have a very low electronegativity, but when we form the cation, what happens is it goes from a larger size to a smaller size. Every time we have a cation form, the parent atom that the ion comes from is always bigger than the ion that it's forming. So our ions always get smaller when we create cations. And the opposite is true when we form anions. When we form an anion, what happens is the ion gets bigger. So we go from nitrogen to the nitride ion. We end up getting a bigger atomic radius. Okay, so cations become smaller. Anions, when they form, become bigger. And what we're referring to is the parent atom for each of those. Okay. All right, so here's your recap. This is all of the, well, maybe not all of them, but most of them. Ionization energy, electron affinity, atomic radius. I don't like that this is backwards, but essentially, this is where it's getting the largest. Okay, up here would be the smallest atom. And the only other one that's not on here is ionic size, because it's a little difficult to put on here. And I think that was it. One, two, three. Yeah, I think that was all of them. But there are other periodic trends. Notice that there's a metallic and non-metallic characteristic. Our most metal element of all would be cesium, and our most non-metallic would be helium. Okay, and we're not going to worry too much about that, but we'll talk about it. We'll actually talk about why metals are, doing what metals do a little later, and a lot of this stuff with periodic trends has a huge impact. I'm talking about acids and bases, so it has a huge impact on a lot of the chemistry that we're going to do. Actually, almost all of the chemistry is going to be affected somehow, some way, based on electron configurations. Alright, so come back to the next video and I will go back and explain each and every one of those periodic trends. But hopefully you've got the periodic trends, at least what they are for right now. Thanks a lot.